So now we move to the second talk, which is going to be given by Antoine from Defense, who is going to be talking about MPC in the wild, architecture and benchmark for key management networks.
Hi everyone. I'm Antoine. I'm a cryptographer at Defense, which is a leading institutional wallet provider, and I would like to talk about like a practical aspects of MPC for securing digital assets. So essentially, the question I would like to discuss with you is how to deploy MPC in the real life. And to do so, I'm going to take the example of a research paper that I published with Jonathan a few years ago about Swiss or the CDSA, and to see what it means to go from a research paper to an actual deployment. So to do so, I would like to start with some reminders about custody of digital assets. It's quite important because that explains many of the design choices we've made. And then we go through the architecture, and finally I would like to share some of the observation and lessons we've learned when deploying these things. So first of all, some reminders. So as you all know here, in blockchain, ownership is derived solely from the knowledge of a private key. And so it's paramount that these keys are kept secret, because if you don't have your key, you don't have your coins. And if someone else has your key, well, you can do transactions, and there is little you can do about it. So having a monolithic private key represents a single port of failure. And so we have seen recently many attacks targeting these blockchain keys through steal founds. And even without attacker, if the key is stored in a single location, whether it is on some hardware device, on the memory or whatever, well, if you lose this key, then assets are lost forever. And I want to point out here that even for MPC, so we have seen recently attacks on AWS data centers in the Middle East, and if for some reason, legal reason mostly, you store all your MPC servers into the same data centers or at its region, well, that can be also a single point of failure, having these things due to external attacks or yeah. So we have an interesting challenge here because, well, on the one hand, you want your keys to be somehow exposed in order to do transactions, right? And on the other hand, for security, you want to keep your keys as inaccessible as possible. So we have an interesting dilemma with digital asset custody between security and usability in general. And so essentially what we want to avoid is having a single point of failure. And so for that, cryptographer come up with a solution, and it is to use a threshold signature scheme, which is a pretty generic and well-known primitive. And here the idea is to take your private key and to split it into a set of key shares. And then whenever you want to sign something, you're going to take a subset of these key shares and run an MPC protocol in order to generate a signature. So when you look at the diagram on the right-hand side, you will say, okay, that's pretty generic, and we as cryptographers are designing this kind of systems all the time. But when it comes to deployment, and especially for TSS, there are different ways to do it. And there are at least two for digital asset custody. The first one is what we call shared custody, where the custody of the key is split between a client and a service provider. And the second one is what we call a defense key management network, where the custody is delegated to a network of servers. So I just want to go through some example of that. So the best way to understand shared custody is to take the example of a wallet application. So it's really the two-party cases that was discussed in the previous talk. So here the user will split its key between its smartphone, for instance, and a service provider using some 2 out of 2 TSS protocol. And so the first share is stored encrypted on the user device and never leave this device. And the other is stored on some service provider. And then whenever you want to sign something, you're going to run a 2 out of 2 MPC protocol to generate a signature. And so this is highly practical for many scenarios, but it comes also with two downsides. The first one is that you are putting a lot of burden on the user that needs to install a special application and somehow manage securely its own key share. And as you all know, most regular people are not super well versed into cybersecurity, so ideally that's something we want to avoid. And a second reason is that availability is not great, because if one of the servers is down here, well, assets are not accessible. So that leads to the question, well, should the user really be responsible for securely managing its key shares? And, well, ideally not so much. Or are they better off outsourcing this responsibility to a group of security-focused companies? And that's what we're seeing at defense. It is like companies are better able to implement strict security controls and also better able to handle like practical things like backups, key recovery, disaster recovery, and all these things. So that leads to the following claim. To securely scale to millions of clients, and especially clients that are not super crypto expert, it's actually easier and preferable to separate asset ownership from the security infra. And that leads to the definition of what we call a key management network, which is essentially a set of servers holding shares of multiple keys on behalf of multiple users. And that follows two main design principles here. So first, as I said, we want to trust the clients as little as possible. So in this setting, a user is gonna delegate its key shares to a set of servers, or alternatively, the servers can run a TKG protocol to generate the shares. And whenever a user wants to sign something, you're gonna do a request, and the MPC server is gonna run the MPC protocol and send back the signature to the client. So obviously, we as a company, we don't really want to trust our client, but also, well, clients, they don't really want to trust the company either. And so to enforce this trustlessness, we can also add things into the mix, like securing the key shares, storing the key shares into our enclaves so that even the company cannot access them. Or the interesting other things about having a network is that we can federate it. So like across different partners or organizations. So like think about having hybrid deployment with some of the servers are stored on-premise by the client directly, or having at least storing the different MPC servers into different cloud providers, or even having different companies running their own MPC servers. So that if for some reason one of the servers go rogue, then the overall security and availability of the network is maintained. And we see a lot of advantages in using this kind of KMN in terms of usability, security, and availability. So the main one is that the overall user experience is unchanged compared to the Web 2 world, right? So users still authenticate using WebAuthn technology, for instance, and so you can seamlessly integrate that into existing flows. Like think about your banks or fintech applications without no need to install any special thing. And also, like there are a lot of blockchain out there with, so a client can have multiple private key, multiple wallets. And so in this setting, it doesn't need to store a lot of key shares. So all the servers are going to take care of this part and only store one single authentication token. And then all the rest, so the refresh of the keys, the recovery process can be handled by the servers directly. In terms of security, so I briefly mentioned, we think that security-focused companies are responsible in this case for securing the key shares. And so rather than the client, which is historically the #1 reason of key loss. And so they can implement very strict security controls like real-time monitoring, anomaly detections, having certification audits, and all these things, and even putting for instance, the key shares into different locations so that to comply with local regulations or law. And the recovery of the keys also is much easier here because you don't have to do any cryptographic operation with the key shares directly, but just give the user like a fresh WebAuthn credential, and that's pretty much it. And finally, yeah, in terms of availability, non-federated solutions seem to kind of inherently require N out of N TSS scheme, which leads to a lack of availability if one of the servers is down. So a quick summary here. So we have a network of servers that stores many key shares for many keys on behalf of multiple users. Now the question is, how do we coordinate or we bridge the gap between the clients and the network in practice? And so in many academic papers about MPC, they're going to author always, and often assume at least, a mesh of secure channels between the parties. And deploying that in practice creates friction in terms of security and complexity. So first, in terms of security, in a peer-to-peer mesh network, every signer also acts as an MPC server. And so they must somehow expose some network ports to the internet to access incoming connections. And that ideally we want to avoid that because that drastically widens the attack surface on machines that are supposed to hold like sensitive cryptographic materials. And in terms of complexity, well, the whole discovery process is more complex here because all the different party needs to maintain and knows, all the rest. And the scalability is not that great because it requires to open n-square connections. So what we're using instead is a star topology where a central coordinator relays the messages between the different parties. And the good thing about that is that in terms of security, now we have only outbound only connections, so that the parties initiate a connection to the coordinator, and we don't have any open ports required on the signers. And the scalability is also a bit better because it requires only n connections, and the discovery process is handled by the coordinator. So you may ask the question, well, we're doing MPC, so we want to distribute a protocol, and we are introducing a central coordinator, but does that compromise security or availability? So for availability, well, the whole protocol is agnostic of the number of coordinators, so we can have multiple ones in order to avoid having one single point of failure. And in terms of security, the short answer is no. We can assume here that the coordinator is fully corrupted by some adversary, and the network as well. And despite all that, the adversary is restricted to a denial of service, again, if there is only one coordinator. So central point possibly of availability, but not security. And so to enforce this trustlessness design, we add a lot of cryptographic mechanisms to the mix, like having end-to-end encryption here, so all the parties are going to run peer-to-peer handshakes through the coordinator to generate encryption keys for the communication. We have strict ordering mechanisms here to make sure that any reordering of the messages are detected by the signers, and also, like for instance, strict context bindings, so that to prevent cross-session replay attacks, because a lot of protocol runs are running in parallel in the real life, and some other stuff. But overall, that really simplified the orchestration and reduce the complexity of synchronizing distributed state in multi-rounds protocols. So here I want to highlight that this can be used for any MPC protocol, not specifically for TSS. And we plan to submit this coordinator-based delivery mechanism to the NIST threshold called as a MPC gadget, again, to kind of bridge the gap between theoretical papers and real-world deployment. So the last part is I just want to give some observation about the deployment and some numbers. So I'm going to take the example of this research paper, which is a threshold ECDSA protocol in the honest modality setting that I wrote with Jonathan a couple of years ago. So we already discussed about ECDSA. So if we remember the previous talk, in ECDSA, the signature is a form of a tuple, RS, where S is equal to the inverse of a random nonce K multiplied by a message or hash of a message, plus this R value multiplied by the private key. And so when you want to go from a standalone ECDSA scheme to a threshold ECDSA protocol, what you need to do essentially is to secret share these two things here. And overall, all the threshold ECDSA protocols follow kind of the same patterns. They all start with a distributed key generation protocol to secret share the private key. So we're going to denote this sharing by the brackets here. So external bracket is the sharing of the private key. And then they consist of mainly two steps. First, a set of interactive rounds, followed by some local computation. So the goal of these rounds is mostly to generate the two sharings that I circled in purple here, which is a sharing of this K inverse and a sharing of K inverse multiplied by the private key. And so to do that, they're going to use different multiplication protocols. So some protocols are using pi-based approaches, some OT extensions, some purely secret sharings with beaver triples. But in any case, they mostly want to compute that. So whenever you have computed that, you have only a local computation of a partial signature that you can then reconstruct. So the first observation I would like to make is that in practice, pre-computation is needed if you want to ensure a low latency for your client. So basically what we want to do is to move most of the heavy operation in terms of cryptography to an offline phase that happens before the message is even known. And we call that pre-signing. And so basically, we're going to split the protocol in two. we have an offline pre-signing phase, and the goal of that is again to generate what you call a pre-signature, which is a triple of three things: R, a sharing of K-inverse, and a sharing of K-inverse multiplied by the private key. And then we have an online signing phase where we're going to use this pre-signature of the message to generate partial signatures. And the good thing about using pre-computation and this offline-online split, and that can really reduce the client's latency. So here I'm taking the example of the CGMP 21 threshold CDSA protocol. And as you can see, it requires almost 1.5 seconds here to generate a pre-signature. But the actual online signing only takes around 80 microseconds. So by doing so, the latency the client sees is really small, despite the heavy cryptography that happens before. Second observation is that the honest majority setting really simplifies the provisioning in practice. So most threshold CDSA papers are studied in the dishonest majority case, so which is really strict in the sense that, we assume here that all parties but one can be corrupt. And in this setting, a pre-signature is again composed of three things, and importantly, they are key dependent. So in practice, if you want to ensure that you have pre-signatures for all keys, you need to prepare pools of pre-signatures tied to a specific key. So for instance, whenever a signing request arrives for the key B here, you consume one pre-signature for this specific key. And if another signing request arrives for key C, then you consume a pre-signature from the pool for the key C. But if no signing request arrives for key A, then you have essentially wasted computation by pre-generating pre-signatures for this key. The good thing about using an honest majority protocol or like your KU protocol is that pre-signatures can be reduced to two things, and importantly, that are key independent. And so by doing so, you can have a giant pool of pre-signatures that works for any key. So whenever a signing request arrives for any key here, you consume a pre-signature from this giant pool. So no need to predict which user will transact next. You can just pre-compute a whole bunch of pre-signatures, and the overall provisioning of the system, it's super easy. Third observation is that we can leverage shared states to improve efficiency. So processing pre-signing requests one by one is pretty inefficient. But the good thing about having first key-independent pre-signatures and our KMN network is that we can generate pre-signatures in massive batches. So again, generating one pre-signature for the CGMP 21 paper takes around 1.5 seconds. For KU, it's slightly better. It's 700 milliseconds because it requires less heavy cryptography, but still it's not great. By doing batching, which is enabled by our batch verification of multi-version triple in our KU paper, we can generate, for instance, a big batch of 10,000 pre-signatures, and here the amortized cost drops to only 1 millisecond. So by doing so, we can really have a very efficient protocol to scale for a very large number of signing requests. And final operation is kind of bit of summary of the three previous ones, is that key independence really unlocks scale when you consider a very large number of keys. So here are some throughput numbers for an actual deployment. So as you can see on the first line, so without pre-signatures, its numbers are not that great. So CGMP protocol requires heavy cryptography, so it's less than 1 signature per second, the throughput. KU is a bit better because, again, it's lighter, but it's still not that much. So with pre-signature, we can say that the CGMP protocol is kind of bounded by a number of available pre-signature. So at defense, we are considering tens of millions of keys. So we cannot pre-compute thousands of pre-signatures per key because that would be like billions of pre-signatures. So it's super heavy in terms of computation and storage. And for KU, we don't really have this issue because, again, pre-signatures are independent, and so we can assume that we can have always pre-signatures available, and so the throughput increase. And we can increase these throughputs by taking larger instances or doing replication, but that's the general idea. So the main takeaway that I would like to make here that in most MPC papers, the threshold transport layer is basically 3 lines on the model subsection. And when you are actually deploying that in practice, we need to treat this transport layer as a real cryptographic component, not just as plumbing between parties. And so our coordinated architecture is pretty practical for that, for actual deployment, and in terms of security as well. And in terms of protocol, I mean, there is no single best protocol for especially CDSA. They all have their pros and cons, but when you want to ensure a very high throughput, our KU protocol is pretty efficient for that. And last remark, again, for standardization, we plan to submit these 2 things to the NIST threshold code. Thank you.
Okay, thank you very much for the talk. Any question from the audience? Okay.
Thank you for the talk. I have a question about when you talk about the network structure with the coordinator in terms of the security. You mentioned that it's not a problem for security, the coordinator, but what about the coordinator being able to partition the network depending on the messages, for example, during the resharing, if you include the resharing in the scheme?
Yeah, so for resharing, it's more difficult because we kind of need broadcast. So we need to kind of add stuff on top of the coordinator architecture to be able to do resharing. So yeah, it's more difficult than just that for resharing, definitely. So because yeah, there are partition issues in practice. So.
Thank you.
Okay. Any other question? I have one question.
Yep.
So you talked about that there's a potential memory storage limit because you could not perhaps store some of the partial signatures as much as possible. Do you have any numbers about like what would be a reasonable storage?
In terms of so depends on your kind of network you are using and use cases mostly because depending on the use cases, the number of transactions you need is very different. But we are seeing more like trading use cases, for instance, that requires a lot of signatures. So yeah, reasonable amount of throughput is 1,000 sometimes signatures per second. And so for that, you need to prepare like 100,000 pre-signatures. It's a reasonable number to have always available to be useful.
And you use rented infrastructure in order to store? Ah, okay. Yeah, so it's usually that.
Yeah, it's always only cloud-based solutions.
Okay.
So, I mean, yeah.
Okay, great. I don't see any other questions, so thank you very much.
Thank you.